I'm Aaron Stump, and today I'm going to present to you our strong functional Perl, Harper's regular expression matcher in Cedille. Harper's regular expression matcher is a continuation-based algorithm for regular expression matching, introduced by Robert Harper in his JFP paper titled Proof-Directed Debugging. And the basic idea of the algorithm is to decompose regular expressions. So you're going to dig down into the regular expression, building up a success continuation. If you detect a clash where the regular expression is asking for some character that's not there in the string, then you just return false. But if you find a character match, then you're going to invoke the continuation to keep processing the suffix of the string. And Harper's paper is, he called it proof-directed debugging because there's an interesting bug in the termination argument for this algorithm unless you use standard regular expressions. So your R star is allowed only if the empty string, epsilon, is not in the language of R. And here in this talk, we're going to enforce that syntactically using a type stdreg for standard regular expressions. And this is an idea we got from a paper from Dan Licata and his students. So here's a look at the implementation in Haskell. We're going to move to the implementation in Cedille in a little bit, but to start off in Haskell, so it's a continuation-based algorithm, so we have a type K for continuations. It takes strings to bools. They're going to take suffixes, tell us whether or not they match. And then there's a type match T for convenience. It just says continuation goes to bool. So here we see the two central helper functions of the algorithm. There's match H. It takes a string and one of these regular expressions, and a continuation. Now, it's the first equation of match H. You see, if that string is empty, then we just return false, because these are standard regular expressions. They cannot match the empty string. Otherwise, we just split the string into its head C and tail C's, and we invoke this second helper function called match I. Okay, and here we see the semantics in the form of these standard regular expressions too. So match I, you can match no match regular expression that just says nothing's going to match, you just return false. There's match car with a character C prime, and then you check, does C equal C prime? And if so, that's the success case, and you invoke this continuation K on the suffix C's. And otherwise, you return false. For an OR regular expression, you just decompose and just check disjunctively the two parts of the regular expression. For the plus case, though, this is where the interesting termination issue comes up. So if we have plus R, we want to match R to see if it matches one time, because this is plus R, of course, being one or more matches. So we match it one time, and then in the continuation that starts out with lambda C's prime, we're going to say, well, let's try just calling the continuation K on C's prime. That would represent exactly one match of R. But if that fails, then we want to go and we're supposed to recursively try the whole regular expression again on the suffix C's prime. So that's what I've got highlighted in red there. And the interesting thing about that, of course, is that the regular expression is exactly the same as we started with. Plus R, we just make a recursive call with plus R. So there's been no structural decrease here, which is quite worrisome for a termination situation. And then concat similarly decomposes and updates the continuation. So the problem of termination for this algorithm has been actually studied by a number of different previous works. You can sort of see the main problem right here in this little part that I pulled out from the code we were just looking at. And so we have match H that calls match I, and match I wants to call back to match H in this red highlighted call site there, but it's calling it with this C's prime. It's just a value it got from a continuation. It has no idea, the code, there's no obvious syntactic connection between C's prime and C's. So it seems that you need something like a proof that the length of C's prime is less than the length of C's or something like this. And in fact, previous works that tackled termination of Harper's regular expression matcher, some of them anyway, use dependently typed continuations. And in fact, one of these papers, a very nice paper I highly recommend by Beauvais, Krauss, and Sozo, raised this challenge that there seems to be no easy way to achieve the same effect without the use of dependent types. So in this Perl, we're showing Harper's matcher as a strong functional program in the sense of David Turner. So the idea is that we want, in strong functional programming, is we want to statically enforce termination of programs. But the name of the game here is you're only allowed to use the types of regular old functional programming, just polymorphic types. You can't use dependent types. You can't use size types. You're not allowed to use termination proofs or variants or metrics or well-founded orders. All that heavy-duty machinery of termination is not allowed in the regime of strong functional programming. And so we are happy to report that in fact you can do this example without dependent types. You can just use the toolbox of, well, advanced strong functional programming. So how can you do that? That's what we're going to talk about for the time we have here. And we're using our language Cedille for this. And so strong functional programming in Cedille. Cedille is a dependent type theory, kind of like Calc or Agda. And termination of programs is enforced by typing. But here, Cedille has some particularities that make it a bit different from Calc and Agda, and one of them is how termination is handled. And that's part of what we're going to have a little tutorial about in this talk. So in Cedille, when you're writing a recursive function, you're presented with something that we call a recursion universe. It's a typed interface for doing the recursion. Okay, so you get an abstract type R, that's what we're sort of thinking of as the universe, the recursion universe, and it has some operations on it that help you write your recursion. You're not allowed to make direct recursive calls in your code. You have to kind of go through this interface. And the language, though, Cedille provides special syntax for these recursion universes that pretty much hide a lot of the machinery and make it feel quite idiomatic way of writing recursive functions. So I want to emphasize that even though Cedille is this type theory that lets you do proofs and things like that, independently typed programs, here we're not using any dependent types or any of that kind of machinery. We're just using strong functional programming. Okay, so let's see how this works in several steps. So the first point, we're going to see the sort of Cedille's recursion universes. So we start off with something called a Mendler-Style recursion universe, okay? And so this is kind of like the underlying interface, and again, Cedille provides sort of a little bit nicer surface language access to this interface, but this is the basic interface that we're relying on. So let's let f be a signature functor for a data type. So, for example, if your data type was list of A's, then your signature function is fx equals unit or A cross x, okay? So if you want to, suppose you're trying to write a function that's going to compute value of type x from your data type D, then what the recursion universe provides you is this abstract type R I was mentioning. It's just some type. You have no idea anything about the type except what the interface gives you about it. The first thing it gives you is an eval function, R to x, okay? And this is the function you have to invoke if you want to make a recursive call. You've got to call eval, but you can only call it on an R thing. You can't call it on just some random other D thing. And you're also given a subdata structure of type fr. In other words, you're given this little package that is presenting you the data that you have, except at the sort of functorial position, it's got the abstract type R. And so the key thing about this is that, and this goes back to this idea of Mendler-Style recursion, is that you can only call eval on subdata, because the only things you have lying around of type R are the things that are hidden, presented to you in this subdata structure, and so that's the only stuff you can call eval on. So that ensures you are doing a structural termination, even though there's no sort of check about, is this variable I'm making a recursive call on somehow structurally derived from my input or anything like that. It's all done through the typing. Okay, so that's Mendler-Style. Now Mendler-Style paramorphic recursion universe. So this is the next sort of step, presenting sort of a conceptual development of this idea of Cedille's recursion universe. So for computing x from data type D, now for paramorphic recursion, the universe gives you the same stuff you had before. The recursion universe has all these same pieces, but it also comes, as I highlighted here in black, with a reveal function R to D. So this unmasks R as really being D, okay? So, but notice you can't go the other way around. You cannot inject D into R. That would be totally unsound from a termination perspective, because you could just stick random values into R and then recurse on them. But here, you are allowed to sort of leave the recursion universe. You can sort of, wormhole out of there if you want to have some data D. And this is really important if you want to write efficient accessor functions like predecessor or tail or something. Now finally, what we need for the Harper's regular expression matcher is we need support for nested recursion. So you have all the same stuff we had before, except we change a little bit. The return type of your function now could depend on D. So you compute x of D from a data type D, and the reason that's really important to shift, as I say below my bullet points there, from x of kind star to x of kind star to star, is that now the eval function, you can write an eval function that goes from R to x of R. And that gives you the possibility of seeing when you return something from your recursive call that it also has type R, and hence you could make a recursive call again on that. So a recursion is then allowed on values that a val has returned. So that enables a form of nested recursion, and the continuations are basically hiding a form of nested recursion. Okay, so let's take a look at how we do this in Cedille, Harper's matcher in Cedille. So the critical part about the nested recursion is here. So in blue, I've highlighted Cedille's syntax for indicating the abstract type R. If we're doing a recursion here, mu match, then mu is for the sort of kicking off a recursion. Then type / match is R. That's the abstract type of the recursion universe. And the X, the type we're computing, here has to be given explicitly. Cedille can't quite manage to infer this for you. And it can mention this R. And that's just like XR or XD. Now we have a way of mentioning, we're indicating the functoriality of X. And X does have to be positive for this to work. And finally, where the eval function is conveniently called match. And so this looks very much like an idiomatic recursion. Now here we're doing something that would be tough to do in other type theories. We're passing the recursive function match there to the helper function match I. But anyway, that match is the eval, and it has the type below. It takes in the abstract type R, which here is denoted type / match, and proceeds. Okay, so that's sort of the setup for the recursion, introducing the recursion universe pieces that we then need to write this helper function and make that deal with that one nasty recursive call. So you can see I've highlighted it here. It's transliterated into Cedille code, but I hope you can sort of still make out the structure. We have a +R case and that I've pulled out here. And we're going to make this recursive call to check one occurrence of R. And then when we make the recursive call, we're calling on match C's prime. And that's great. This match function is actually coming in to match I, as you saw, where match I is invoked on my previous slide. The match function is coming into match I, and it's expecting type T, where T is actually just some abstract type. We really don't need to know much about it, except we can recurse on it. If you're looking at the type signature of match I at the top, we can recurse on it, and the suffix comes in at that type. And so when we call match of C's prime, match is expecting input of type T, and C's prime has type T because C's prime is the input to the continuation, and the continuation, as I noted there in blue, has type KT, which is T to bool. Okay, so to conclude, we talked about Harper's regular expression matcher, which uses continuations for a very elegant control flow that leads to complications for termination reasoning. And we saw a solution now using strong functional programming in Cedille. It's type-based. There's no fancy extra additions beyond regular types of functional programming. No dependent types, nothing like that, even though Cedille does support those separately. So we use this idea of a recursion universe that gives you a form of sort of type-based nested paramorphic recursion. And it turns out that Harper's matcher is just a perfect fit for this. It's very easy. We don't have time to wade through all the code, but it's really pretty much a direct port of the Haskell code because of the way that the abstract type for the eval function matches up perfectly with the inputs for the continuation. So thanks very much to funders, and I'd really like to thank the very dedicated anonymous ICFP peer reviewers who gave us outstanding, really above and beyond kind of criticism and help getting this into good shape, and Shepard Richard Eisenberg, and colleagues here at Iowa, and thanks to you for watching.